Everyone, I'm Matthew Jagelski, and I'm giving the teaser for Auditing Private Machine Learning, How Private is Private SGD. This is joint work with Jonathan Ullman and Lena Opre, all of us at Northeastern University. This talk concerns differential privacy, a probabilistic notion of data privacy whose strength is parameterized by some value epsilon. The lower epsilon is, the more private, but also potentially the less useful the algorithm is. DPSGD is a popular private machine learning algorithm which adapts standard SGD to a differential privacy constraint. The way it does this is by first clipping gradients and then adding noise in every iteration. Setting epsilon is even more challenging for DPSGD because we don't actually know what epsilon is. What I mean by that is that a privacy proof will only give an upper bound for the true privacy level. Improvements to the proof will get closer and closer to the true value of the privacy laws. However, to understand the limit of where this can go, we can use privacy attacks to get lower bounds on this true epsilon. The current gaps between the best attack and the best analysis, though, are off by a factor of around 100 or even more, making setting parameters really difficult in real deployments. This raises the question, how closely can we get to this true epsilon value, the true privacy loss of the algorithm? This is where our work comes in. We show that it's possible to audit private machine learning algorithms using poisoning attacks, which are corruptions to the training data set that are used to change the model. We show that existing poisoning attacks aren't sufficient for DPSGD due to gradient clipping. And so we design novel attacks that are specifically tailored to DPSGD. We also show that our attack is dependent on parameters that aren't used in the analysis of DPSGD, which means that the analysis could be improved in the future by incorporating these parameters, potentially. Now we'll give you a basic idea for how our auditing algorithm works. We start with a standard data set. This could be MNIST, CFAR, whatever you want. And then we carefully construct a set of poisoning data and add it to the data set. Basically, if the algorithm is very private, it shouldn't reveal that the data set is poisoned. So we run the algorithm many times, measuring the poisoning effectiveness of each model. We'd expect the poison data to result in more poisoned models, and the extent to which that is the case, that is, the accuracy with which we can guess whether a model was trained on poisoned data, allows us to compute a lower bound on epsilon. This is an example of our auditing algorithm in action on the fashion MNIST dataset with the neural network model. Our attack, the clipping-aware backdoor, improves on the standard membership inference attack by a factor of more than 10 and gets around a factor of 10 away from the theoretical upper bound. To learn more about our auditing approach, come check out our poster.